Hi everyone. In this lecture, we'll discuss about the non-ideal capacitors. Okay. So for example, consider an ideal capacitor which is charged to a voltage, say Vx volts, and then I connect after some time a load resistance RL across this. Now, if I keep reducing RL, so what one would expect is that if I try to plot the power dissipated across the load resistance. So since we have already done RC circuits extensively, we know the voltage will start from Vx and go to 0 eventually with the time constant given by RL into C. Similarly, the current will simply start from Vx by RL and go to 0 eventually. And the power, we know that starts from Vx square upon RL and would eventually go to 0. But in this case, the time constant is going to be tau by 2. Time constant, I am calling it as tau dash, which is tau by 2. Now, as I keep making RL negligibly smaller and smaller, the peak value will keep increasing, the peak power value will keep increasing, and the time constant will keep reducing. Eventually, in the limit RL tending to 0, we would have an impulse of power transmitted from the capacitor to the load. So it loses all the energy in no time. So that's why we get a power as an impulse function. Now we can also show this is nothing but half CVx square into delta of t. We have already done that in the previous lectures. Now this is an ideal capacitor. So meaning it can actually deliver infinite power, okay, if the load demands it. But any practical capacitor cannot deliver infinite power. And we discussed in the previous lectures, to capture the effect of finite power, we normally model a series resistance Rs. So the series resistor Rs here, I'm going to call this as CS to just say that they both are in series, a capacitor of value CS with a series resistance Rs. Now by connecting Rs, I'm capturing the finite power nature of the capacitor. Okay. So again, just to clarify here, so when we began the series of lectures, I discussed that a voltage source Vx, when you connect it to RL, okay, by definition, as I keep making RL negligibly smaller, the current delivered by an ideal voltage source will tend to infinity. But to model the finite power nature of the voltage source, I said we model a finite source resistance Rs. Okay, so this actually captures the finite power, that is, the voltage source can only deliver finite power. That effect is actually captured by adding a series resistance. But still, in this model, the power is delivered constantly, which means the energy can be infinity. So this voltage source is actually a voltage source which can actually deliver infinite energy. Okay. To model a finite energy source, then we'll have to model a voltage source as a capacitor with a value C. Okay. And as I discussed in the beginning, in the initial lectures, voltage sources are normally characterized by represented by what you call as the watt-hour units, or okay, they are specified by their watt-hour units or ampere-hour units. And I said watt-hour represents the energy. Okay, so we have already discussed about that extensively. So if you want to model a voltage source as a finite energy source, then we'll have to model that as a capacitor. And to capture the finite power nature of the voltage source, then we'll have to model them with a series resistance. So this model captures both the finite power and energy nature of a practical voltage source. Okay, when I say practical voltage source, like a battery or a charged capacitor. Okay, so this the model shown here captures that. Also, practical capacitors also come with finite series resistance when we are using them in oscillators, digitally controlled oscillators in RF circuits and radio frequency circuits. So even in those applications, one is interested in knowing what is the effect of the series resistance on the overall the capacitor behavior. How does it change by adding the series resistance, and how can you quantify that? How good a capacitor is, how can you quantify that? Okay, so that's something we are more interested in knowing. Now, in a similar way that we described in the previous lecture, I am going to define a parameter called Q. So when two elements are in series, I said the element with a higher impedance should always dominate. So here the capacitive impedance is 1 by omega Cs, and we want 1 by omega Cs to be as high as possible. For all the frequencies of interest, we want this element to behave like a capacitor. Okay, so for that, the complex part of the impedance, or the reactive part, the impedance of the capacitance, should be much greater than the impedance of the resistance. And I'm going to divide this by the series resistance, so you're going to get 1 by omega Cs Rs. So this is the series Q, I'm going to call it Qs, of a series RC circuit. Now the proof of, we can also define Q in a similar manner how we define for inductors. I can first inject a current, a sinusoidal current, and then try computing the power dissipated across the resistor and the capacitor. Now we know the power dissipated across the resistor is I naught square R into sine square omega naught t, and the power dissipated across the capacitor, first you have to find the voltage, which is 1 by C integral of the current. Okay, so you are going to get I naught by omega naught Cs into cos omega naught t. So the integral of this, you'll have to multiply it by sine omega naught t. Okay, so there will be I naught square here. So again, I just got this result by multiplying the voltage and current across the capacitor. So this result will simply reduce to I naught square upon omega naught Cs into 1/2 of sine 2 omega naught t. Okay, so I think there is a minus sign here, because integral of sine is minus cos. So you get this result here, and similarly I can calculate the peak to peak power dissipated across the resistor. Again, you can see the power dissipated across the resistor in a single cycle is 0. In one cycle it will deliver power, in the other cycle it will absorb power. So the net power dissipated in a single cycle is 0. Okay, so I'm going to take the peak to peak value of the power and then take the ratio for the series, the power dissipated, the peak to peak value of the resistor power, and I'll get 1 by omega naught Cs Rs. So here it is Rs here, I'm sorry, it should be Rs there. Now this is for a capacitor with the series resistance, and again the Q which we defined is actually 1 by omega Cs Rs, and this is again a function of frequency. So at lower frequencies Q is very high, and at higher frequencies Q reduces. And again that should be pretty obvious, because at lower frequencies the capacitive impedance is much higher compared to the resistor. So therefore the capacitor will dominate, and so which means it's behaving like more and more like a capacitor. At very high frequencies, when the capacitive impedance becomes very small, the series RC network will behave more closer to the resistor. So therefore that Q will be very, very less. Okay. The next thing is, similarly we will start with the parallel RC network, so wherein we can have a capacitor CP, RP. Again, parallel resistance is also modeled. For example, if you charge a capacitor and leave it open indefinitely, so there will be some leakage current across the capacitor which would slowly dissipate away the energy. Okay, and that can be captured by modeling a parallel resistance RP. Okay, now in a similar manner we can actually try to compute the value of Q. So in this case, as I said, when two elements are in parallel, the one with the higher conductance is going to dominate. When you compute the overall conductance, the one with the higher conductance is going to be the one which is going to dominate the overall conductance. So I am going to take the ratio of conductances. So that is omega Cp is the conductance of the capacitor divided by 1 by Rp. So you will get omega Cp Rp. Again, ideally you want this element to behave like a capacitor, and that will be possible if Rp tends to infinity. If Rp tends to infinity, Qp, here the Q is the parallel Q, will tend to infinity. Now I can also find the value of Q by using the power dissipated across the resistor and capacitor method. So you can just take the ratio of the power dissipated across the capacitor divided by the loss in the circuit, which is the power dissipated across the resistor, the peak to peak values. You will get the same value here, omega Cp Rp. So here in this case, since both the elements are in parallel, you have to apply a voltage source. I'll leave the exercise to you. It's a very simple thing to show. So if I apply a voltage source of value V0 sine omega naught t, you can very easily show that the Q P, which we obtain by taking the power dissipated across the capacitor, the peak to peak value divided by the power dissipated across the resistor, which represents the loss, will be omega Cp Rp. Here it is omega naught because I've assumed the frequency to be omega naught. The parallel Q actually is proportional to the frequency. So that's something to keep in mind. And finally, we'll go back to the series parallel conversions. So a capacitor Cs in series with a resistance Rs can be equivalently converted to a capacitor and resistor in parallel. So Cp and Rp in parallel. Okay. So now to find that value, I can simply equate 1 by j omega Cs plus Rs. I'll take the conductances of the two elements, so which will be 1 by j omega Cp plus 1 by Rs and the inverse of this. Now all I need to do is equate the real and imaginary parts. So I'm going to take Rs common out. So I'm going to get something like this is Rp. Okay, and I'm going to use the result. Okay, in this case we'll try to find the equations for Rp, and we are more interested in finding the equations for Rp and Cp in terms of Rs and Cs, okay, and Qs. So if you are interested in finding that, then I think we should rearrange the other term. Okay, even this we can actually get relations in terms of Rs. The equations for Rs and Cs in terms of Rp and Cp. Okay, so by doing this way, so if you see this result, omega Cp Rp is actually Qp. So I'll get Rp upon 1 by Qp square minus Jq into Rp upon 1 plus Qp square. So I'm going to multiply and divide by omega Lp, omega Cp, so then I'd get Rp by 1 plus Qp square minus, so then we know omega Cp Rp is actually Qp, so I'll write it as minus j, or I'll write it as 1 by j omega Cp into 1 plus 1 by Qp square. So we got two interesting results here. So Rs can be represented in terms of Rp as Rp by 1 plus Qp square, okay, and Cs can be represented as Cp into 1 plus 1 by Qp square. Now in a similar way, I can just rearrange the terms. I can just in this equation I can take this term to the denominator. This term I can flip it here, and then I can take this term on the other side, and similarly derive expressions for Rp and Cp in terms of Rs and Qs. I'll give the final expression. Rp will be equal to Rs into 1 plus Qs square, and Cp will be equal to Cs by 1 plus 1 by Qs square. Now you should understand that your Qp is actually omega Cp Rp. Okay, so in place of Rp, if I use Rp as 1 plus Qp square into Rs, 1 plus Qp square into Rs, and Cp as Cs by 1 plus Qs square or Qp square, I'll actually get this result, or I'm going to use, this expression is in terms of Rp and Cp, so I can use, in place of Rp and Cp, I can use these two expressions, and I'll actually get Qp equals Qs. Okay, So since QP equals QS, these two equations are the same. I mean, whatever these two equations are saying, they're actually, the set of equations are the same. So in the last lecture for inductors, we did the opposite. We tried to find RP and CP in terms of RS and CS. In this lecture, I wanted to show RS and CS in terms of RP and CP. All I'm trying to show is it's the same. I mean, because your QS equals QP. Okay. For the parallel Q and this, the QS is actually the same. So when you convert a series RC circuit to a parallel RC circuit, the Q you compute for both the circuits, even though the equations are slightly different, the final result is actually the same. When you actually modify and when you actually, after some simple algebraic manipulations, you can actually show QS equals QP. Okay. So again, you can easily verify. Here I have modeled a capacitor in series. For example, the impedance of this network at DC is infinity, right? At omega equals 0, for a series RC it's infinity. But when you look at this network, at DC it's simply equal to RP, because this capacitor just opens up. But then you have to understand your CP is actually CS by 1 plus 1 by QS square. It's a frequency dependent capacitor, and QS actually depends upon frequency. Therefore, it's a frequency dependent capacitor. Okay. And similarly, RP also is a frequency dependent resistor. It's not just a pure resistor, but a frequency dependent resistor. At a single frequency, yes, we can model that as a lossy element as RP, and then a loss, and the energy storing element as with the value of CP. Okay. So the value of RP is again RS into 1 plus QS square. Now the QS, value of QS is actually 1 by omega CS RS. This term at DC will tend to infinity. So your RP will tend to infinity. Okay. And similarly, your CP will tend to CS. So at DC, this circuit, the parallel RC circuit, will simply reduce to a single capacitor of value CS. In the same way, this network at DC at low frequencies, I can ignore the resistor. The series RC network can be approximated to a simple capacitor. So therefore, these two circuits are equivalent. Okay. So this model is actually valid for all frequencies. The equations that you have written here, it's valid for all the frequencies. Okay. Here, because QS and QP, they are actually frequency dependent values. So when you convert a series RC circuit to a parallel RC circuit, the R and C values are actually frequency dependent. So that's something to keep in mind. Okay. So just to summarize, we just discussed the Q for a capacitor. Okay. And we defined QS, the series Q, as by the ratio of impedances, which is 1 by omega CS into RS. And we also said a series network can be converted to a parallel RC network. Okay. And we define QP for that as RP CP into omega. Okay. And we showed that when you make a transformation from a series RC to a parallel RC, your QS will be equal to QP. Whether you define it for a series network or the parallel network, the Q will remain the same. Okay. The Q tells us how good a capacitor it is. Okay. So this is just a different model, but we are just doing a different model for the same capacitor. So that should not change the value of Q. So that's the important point to understand here. And we also showed the conversion relations for CP as CS by 1 plus 1 by QS square, and RP as RS into 1 plus QS square. Again, for an ideal capacitor, RS should be 0. If RS is 0, then RP will actually be infinity. When you actually make this conversion, you can easily show if RS is 0, QS is infinity, and even though RS is 0, this result will tend to infinity. Okay, for a parallel RC network, for it to have no losses, RP should be infinity. So these equations will capture that. Okay, so that's all about capacitors and non-ideal capacitors, and how to model or how to define Q for these non-ideal capacitors. And we will be using the analysis of non-ideal capacitors probably, when we are analyzing RC circuits or voltage regulators, or even in RF circuits, when you are analyzing digitally controlled oscillators, LC oscillators, where normally you have a capacitor bank. So your frequency is tuned in this fashion. You will have a single inductor and a bank of capacitors which are turned on and off to get the desired frequency of oscillation. In that case, the switch resistance will come in series with the capacitor. Okay, and that actually has, it's a little bit more complicated analysis. It actually has an effect on the overall noise of the oscillator. So it's important to model the series resistance, and it's important to know some parameters which can tell you how good your capacitor should be. Based on that, you can design your capacitor. So we talk in terms of Q. Instead of talking about series resistance Rs mainly, we will directly use the word Q. Okay, if you want to compare two capacitors, I'll just directly use the word Q to compare how good of two capacitors of same value. If they are having different Qs, then the one with the higher Q is a slightly better capacitor. So that's the conclusion from this lecture. So I'll stop at this point.